So, for those of you who have seen it, perfect, you can just solve the exercises and be happy. If you need some refreshing, here we go. I'm going to first take different examples that are simpler than the examples that we have here on the slide. These functions are pretty ugly again. So chain rule, if you just look at the formula, looks scary, and we still don't get much what this stuff means. So I just wanted you to have the formula to later, when you get the idea, come back to it. So what we're supposed to do, let's take an example that is very, very simple. 3x to the power of 4 plus 5 to the power of 6. Okay, so what you see here is a function inside a function. So we have the power, which is a function, right? So something to the power of 6 is a function. And we also have 3x to the power of 4 plus 5. So how do we take a derivative in this case? We cannot just take a derivative of this, right? Because we know that it's to the power of 6. If it was to the power of 2, we could probably just expand it using the Newton's binomial for the second power, but here we cannot do much. Well, we can still use Newton's binomial, right? But we don't remember it, and I told you not to learn it by heart and whatever. So there is a way to always calculate the derivative of a function that is inside a function. You can have actually third function inside. So it's like, you know, Russian doll. Okay, so first of all, what do we have here? We have the function, let's call it g. Function g is just what I have inside. So it's an inner function. I'm going to use this terminology. I have no idea if it makes any sense, but now to you it does. Inner function is this one. So it's the function then afterwards we do something else with this function. So in this case we raise it to the power of 6. Okay, so let's call it like that. And then you can see that actually y is something like f of g of x. And what is f doing? The f function is putting everything, like let's say f of y, well, no, of x, right? So normally function f is just x to the power of 6. And when we put instead of x another function g, that's what we get. Sorry, this is not supposed to be like 6. Okay, perfect. So this is this part on our slides. Just to, for you to understand the formula. Okay, perfect. So we have inner function and outer function. The formula tells us first take a derivative of the outer function with respect to the inner function, and then take the derivative of the inner function. That's what we're gonna do. So y prime x equals to the derivative of the outer function, something that is raised to 6. It is 6 times this something, in our case it's a function, raised to the power of 5. So you can just look at this and recall this is the simplest derivative we can think of. So we're taking the derivative of an exponent, right? Okay, and that will be, instead of x, I'm just writing this because I'm now having a function of another function. Okay, perfect. That we did the first part. Now the second part is the times the derivative of the inner function. and their inner function is 3x4 plus 5, so the derivative will just be 12x cubed. Perfect. Great. Okay, that's it. So with this simple example, it works this way. Let's take another simple example where y is equal to, which one? No, this one is good. X to the power of 5, x squared, which actually doesn't matter at all, plus 3x plus minus 1 to the power of 5. Okay, cool. So this one, the outer function is 5, and the inner function is this. Then y prime x equals to 5 of all this to the power of 4, because the first step we're treating everything that is inside as big X. And then we do it times, and now we're gonna take the derivative of the inner function, and it's just 2x plus 3. Okay, that's how it works. Let's see what else can be inside. Well, y equals to logarithm of 2x plus 1. Okay, well, this is a real deal, because before we could probably expand it some way. Here we cannot do anything. And we know that the derivative of logarithm is 1 over x, but what if we don't just have x, we have something else? So the outer function here is derivative. And we know that as I already said, times the derivative of logarithm is just 1 over x. Only that now we don't have just x, we have 2x plus 1. And we treat it as one big X. And now we multiply it by the derivative of this big X, which is 2. Right? So again, simplified, otherwise it looks too bad. But that's the idea. And on the slide, what you have is super huge, especially this one. It's awful, right? So you have here outer function sinus, inner function this stuff, and then inside you have a logarithm, but not just that, you have another one. Wait, where is my zoom? The third example, which one is the inner and outer function? Okay, in the last example here, third, yes, actually a good idea to do this. So here the outer function is logarithm. Why? Because it is the last thing that happens to x. So it is like, if you recall yesterday's inverse, we say what happened to x. First, what happened to x was doing 2x plus 1. Second, what happened to this whole thing was taking the log of it. So we start by the last operation. In here it was cube. In here it was fourth power. In here it was sinus. In here it was a square root. In here it was the weird square root fifth power. Okay, so that's the idea of chain rule, and actually, well, you'll see that it gets a bit better. I have to warn you right now, this, I mean, not warn you, but kind of make you feel a bit better. You will never see these monstrosities in your micro. The worst that you can see is this. Obviously this, yes, certainly everywhere, but don't, don't get super scared if, for example, right now you didn't get this one correct. I gave it, well, the sinus is the advanced level. More in terms of being careful. So for me, this is the killer. I don't know how to write it. Good thing that I have it prepared something. Okay, so now I'm giving you some time, right? I don't know how much time you need for this thing. Let's consider another example, okay? Before I give you some time, so you see better how it works, just to refresh the thing. Okay, now I'm gonna take something like e to the power of x 2x plus 1. I like 2x plus 1. 2x plus 1. Okay, so here the outer function will be the exponent. So the last thing that happened to whatever expression of x, it became a power of exponent. So we're gonna say, well, the derivative is, we're taking first the derivative of exponent. The derivative of exponent is what? Is itself. And now we're considering everything here as just big X. And we're saying, well, that's it. We like it. We know it. Then times, and now we're going to take the derivative of the inner function, which is just 2x plus 1. So that will be times 2. And what else? No, I have with powers, but logarithm, exponent, square root. Okay, so y is equal to square root of not just x, but of x squared plus x plus 1. Ooh. So here, the outer function is a square root. We know that the derivative of a square root is 1 over 2 square roots. And we have to write the whole thing there, because that's, for now, we just consider it one big X. And now we say, okay, time to take the derivative of the inner function. 2x plus 1. Okay, perfect. So now go on. I'm giving you, I think 10 minutes is good for that. I'm giving you 10 minutes. And yeah, if you solve them already or solve them faster, just chill, okay? So here is the example that I'm gonna leave in front of your eyes. We have example 3, 4, 5, the most difficult, like, okay, like that is good, I think. Like that is good. Okay, so at 54 we're going, okay, let's check. So the first one was not that bad. So let's call it slide, which slide is that? 8 solutions. That was supposed to be, well, at least what I got, minus 3x squared minus 2x plus 3 squared times 2x minus 2, 2x minus 2. Okay, all good for that one? Yeah, now I will need a lot of pluses all the time. Okay, seems like all good for this one. Now for the second one. Wait a second. Okay, place that. This is, okay, for logarithm, logarithm of 2x plus x, all that will be to the power of 3, then times fraction 1 over.
When do I give you the thing? You have the adapter?
2x squared. Who has the unmuted microphone?
In my room, it's 163.
I don't even see who has it. I'm typing. Okay, times 4x plus 1. Who? Okay. X, yeah. Well, that was just. Okay, so, is that good? Plus, minus. Okay, I have many pluses. So look, if, wait a second. Yeah, perfect, okay. You can have more than just two functions, outer and inner. You can have one inside another, inside another, inside another. And you just have to multiply them one by one by one. Okay, cool. So now, how many chains are there in 2? How many chains? How many stages? Well, we would say 3, right? Because we took 3 derivatives. That's what I would say. Oh, cool. You're welcome. Now this. Okay, it's gonna be long. Cosine. Because that's just the derivative of sine. At least here we have something that is not so difficult. We just have to rewrite the whole thing again, but well, logarithm of 2x cubed plus fraction 3 over x plus 2 cube. Tap. Oh, how beautiful. Okay, great. Now that we have to multiply by the derivative of the inner for sinus function, by the derivative of this thing. This thing is a sum of two things, so we'll have first 7, then plus, and the derivative of the log is just 1 over whatever is inside the log. And here we have so many things inside the log, but well, can I? Yes, I think I can, right? If I copy this, will it copy beautifully or no? Yes, okay, perfect. So that is the second one. Now we have to multiply it. So we did this, right? We took the derivative of this part. How do I do it? Okay, I don't have to have this whole thing. Whoa. No. I don't have to have this whole. Okay, perfect. So, okay, right now this is going to be better. Okay, cool. So, I think what I have is the derivative of inside the log. And the derivative of inside the log, so the derivative of this is, let's see, it's another fraction. And another fraction will be 6x squared minus, wait a second. No idea. The way I see it is everybody is muted. Ah, no. Okay. Yeah, I found it. I found it. Sorry. Okay, cool. 6x squared minus the fraction of, I'm gonna get back here and tell what is what. So that will be 9 over, just for those who did it, please check. Squared, no, not squared, 4. Okay, and this one is 2x cubed plus 3. Oh, that's another fraction, right? 3x plus 2 cube. Okay, so perfect. Now you see the whole thing. And there's for sure a problem. Okay, yeah. Prodipto, you may unmute. Let's see. What did I do? Let's just, okay, so you keep your microphone and instead of this one, this expression. Okay. And then here I have 1, consequently, right? Okay. Okay. Put pluses. If you agree with this one. Okay. Yeah, I see where I got this double thing, because what I did was confusing with the sum. Okay, perfect. So now let's explain it to everybody. At least we have 2 correct ones. So the first one is cosinus. That's easy. So we just wrote the, okay, cool. We just wrote the cosinus of everything that is inside, and that is this part. Okay, now the second inner function, and here what we should realize is that this inner function is a sum. I said it. Perfect. So, how do I take the derivative of a sum? I take the derivative of the first part, that is 7, and then I'm going to take the derivative of the second part. And the derivative of the second part is, well, let's write it more like step-by-step manner. That would be like that. So, what happened? This, the whole second parenthesis, it is the derivative of this thing. Okay? So, I took the derivative of 7, it just left 7. Then I was supposed to take the derivative of this. Here I see that I can apply chain rule. So I do first, I'm saying, okay, the outer function here is a log, perfect. So yeah, I see what happened there. I know, I copied and it went bad. Let me finish the explanation. So with the 7x we dealt, it's just 7, and then this, the derivative of this, we see that the outer function is the logarithm. So okay, perfect, we're like the derivative of this will be this, right? Well, this is just how logarithm work. And then what I'm going to say, well, let me take then the derivative of the inner function, finally. And the derivative of the inner function will be 6x squared minus 9 over x plus 2 to the power of 4. So this parenthesis is just the derivative of this thingy. And then since it was inside the log, we have to add the derivative of the log. Okay, so now it looks good. Wait a second. I have one message. Yeah. So is that okay? Add the derivative of the log? Well, yes. So if we just consider this part, okay, focus here. The outer function is natural log. The inner function is a sum. It's quite simple. Then the derivative of the log will be 1 over this whole thing. That's this part. And the derivative of this parenthesis, we have to take it. So that will be 6x squared minus, well, here we have x plus 2 to the power of 3. And the derivative of this second fraction will turn into this fraction. Okay, was it clear? Or I just said the same thing and it didn't help much? Okay, perfect. Okay. 4 packages in total. Yes. Well, no. I don't know. It's just because of this sum we could get confused. Technically, we have outer sign, and then we have inside a sum of something that is just normal function and another package of 2. So you could say that it's 4, but yeah. But after all, you see that we got a product of just 2, 1 and 2. And the second product has a product inside of it. I mean, the second element has a product inside of it. But I don't know, do you need to know how many stages there are? You just take them one by one and I can understand that you need to know how many products you get in the very end. Well, in this case, it is more like 3. Yes, this is the final answer. I know. Crazy, right? You will not see anything like that. It is just for you to get inside the chain rule. Why was the term minus after 6x squared in the last term? Okay, why do we have this minus, right? This minus comes from the fact that in the beginning here we had a fraction, so the actual power of x plus 2 is minus 3. And what we have to do is always multiply coefficient by the exponent, so it was 3 multiplied by minus 3. And we got minus 9, so we got the negative one. Is that clear? Great. Wow. 4. It's better. It's just like 2 things, right? So we have a fraction of 1 over 2 square root of e to the power of x plus sinus 2x parentheses. Okay, we have to multiply this now. So this is just the derivative of a square root. So if we had x here, we would do 1 over 2 square root x, and we consider this whole expression for now as a big X. And we write it here. Then we're like, okay, times. And then inside this times, what do we write? We write the derivative of e to the power of x plus sinus 2x. The derivative is e to the power of x plus cosinus 2x times 2. What happened here? It's like the sum of two functions. One of them is normal function, another has inner and outer function. So for the sinus, the sinus was an outer function and 2x was the inner function. We took first the derivative of the sinus and we considered 2x as one big X, and then the derivative of the outer function, so we have 2. Okay, is that correct? Pluses. Okay, wow, good. Good. Yeah, I know it's correct. 5. Where the 2 comes at the end. Okay, this one, it is nothing but the derivative of 2x. So if I just ask you, please take the derivative of this sinus 2x, you will see that there is an outer function sinus, and inside I don't just have x, I have 2x. So it's a function inside the sinus, and I was supposed to take a derivative of that too, according to the chain rule. So first it was the cosinus of 2x, and then it was 2 because 2 is a derivative of 2x. We should not forget about it. So given here inside we had just x, then we wouldn't have to put this times 2. But here we will also have just x. So this 2 is the derivative of that inner function. Perfect. And the last one, where is it? I have more. It's supposed to be a function in sinus as soon as the x is not standing alone. Yes, as soon as a constant is with the x, we need to see if it's a function, right? Yes, as soon as something is with the x. So the simplest, actually, inner function is, wait a second. For example, here, before going to 5, let's compare the derivative of x to the power of 5 and the derivative of x plus 1 to the power of 5. Okay, so the first one, we should name it f. So the derivative of y with respect to x will be 5x to the power of 4. Here we have something inside it that is x plus 1. So here we're supposed to consider this, the derivative of this thing will be x plus 1, 5, sorry, x plus 1 to the power of 4. And now we are like, well, we're supposed to take also a derivative of the inner function because we don't have just x, we have something with x. And the derivative of the inner function here will be just 1. And that is what is happening in our normal functions, right? Because the derivative of x is 1, That's why before we were never thinking of it. But technically, even x to the power of 5 can have this inner 1. But anyways, once I have here, for example, 2x plus 1 to the power of 5. Here again, the derivative is 5x to the power of 4 versus this derivative that is, now we have Now we have 5 2x plus 1 to the power of 4 and times 2 because, well, now the derivative of the inner function actually is not 1, it's 2, and we should not forget that. But, well, that's pretty much the difference between having an inner function like here and not having an inner function like here. Alright, so perfect. Let's do the last one. I don't know, I lost it. Okay, I have to do it with you. So now the way to see it better would be to rewrite it as 5 times x plus ln x to the power to the power of 1 over 5. Okay, do you agree with that first of all? Okay, you do. That's great. So then I can think of it as, well, let's take a derivative. So the derivative here will be the outer function is power. So the exponent 1 over 5. And certainly the coefficient 5. So as a derivative of the outer function, we'll have 5 times 1 over 5 x plus ln x to the power of a fraction, and the fraction will be 4 over 5 and it will be negative 4 over 5. Okay, that's just the derivative of the outer function. Now the inner function, x plus ln x. Well, for once, it's not that difficult. We have here 1 plus the fraction 1 over x. Okay, cool. So that's it. Do you agree? Plus, 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 plus. It is minus 1 over 5. Wait. Here it was negative. That's what you want to say. Okay, here it was negative, obviously. So here what we got was minus 6 over 5, right? Okay. Minus 1 over 5, yes. And it is minus 6 over 5, right? In the answer. I mean, in the derivative. Minus 5? What's minus 5? The coefficient, yes. Well, technically, this part is with minus. So, if I'm writing it super detailed, let's write it super detailed. Okay. Now, is it good? You got the same? Who else got the same? Yeah, great. Thank you. So yeah, here it was supposed to turn, well, 1, right? And then nothing much else to simplify. Yeah. Okay, cool. Great. Implicit function rule. Obviously, I'm giving you more homework to train chain rule, and it will not be as bad as this one. Maybe I'm gonna give you just one as bad, but in general, I'll try to find the functions that look like something that you're gonna see in micro. Like, usually it's just 2 steps. 3 steps is an exception. Okay, implicit function rule. So here, for a second, we should imagine a situation. So what we can have is not a function of y expressed in terms of x, but just some relation that is expressed in the form of an equation, and you can think of, well, for example, when we have what can we have? Marshall and demand. So it is a quantity of good as a function of prices, price of this good, price of the other good, and the income. So income is usually fixed, but price of this good and price of the other good, well, price of this good is a variable, price of the other good will be also fixed, but we understand that we can change it, right? So given we want to find the derivative of our Marshall and demand of good 1 with respect to, for example, the price of the good 2. So we can re-express one in terms of the other, or we can use the implicit function rule. And it is actually quite great, because all you have to remember is this formula. If you don't even understand how it works, you will always get your derivative. So look at this. In here, I could go through, let's express y in terms of x, and then just take a derivative. What's the problem, right? But well, first of all, it is kind of a problem here. We'll have, well, you know, like here, for example, not that easy. So let's see why the implicit function rule works. I'm going to show you one example, because what I could ask you here is just, okay, use the implicit function rule to find the y prime x, and just do this all the time. But let's see why it works. So imagine we have something like x squared plus y squared equals 1. So we want the derivative of y with respect to x. Okay, great. Great. We don't have y expressed in terms of x. No problem. Let's think of what are we doing with this equation. We are pretty much taking the derivative, the first derivative with respect to x of both sides of this equation. So let's let's do this. And now I'm going to use, no, I'm not going to use anything. So x squared plus y squared prime x. So I'm going to keep this notation for now because I don't want to confuse you with too much difficulties of total derivative, partial derivative. Just let's see. Okay, well, we're gonna take the derivatives of everything with respect, also the derivative of 1 with respect to x, we're gonna take. Cool. So with the left side we can work a little bit. We're gonna have our x squared prime x, so the derivative of this function with respect to x we're gonna have, and then the derivative of this function y squared with respect to x. For now it makes sense because we're just not doing much, but let's see. So it was the derivative of a sum, and we know that we can split it into a sum of two derivatives. Cool. Now with the right hand side I already know the derivative of 1 with respect to x. 1 is a constant. So the derivative with respect to x will be equal to 0 because, well, there is no x. Now, the derivative of x squared with respect to x, well, that's 2x. And the derivative of y squared with respect to x, well, here is the deal. We don't know what's y, but y is going to be a function of x. What we wanted in the beginning is the derivative of y with respect to x, thinking that y is a function of x. So in here, what we pretty much have is our chain rule hidden, because just the derivative of y squared will be 2y, but then we have to multiply it by the derivative of y with respect to x, because y is a function. We don't know which function. So if we knew it, perfect. We would take this derivative straight using chain rule. But we don't know, so that's how we write it. Okay? And this thing is equal to 0. Oh, great. So we just ended up with this. We wanted it since the very beginning. Okay, well, let's do it. So now we just have to extract this. I'm going to write it step by step. Y prime x minus, minus 2x. So y prime x equals minus fraction of 2x over 2y. So it's just minus the fraction of x over y. Okay, so perfect, we got something. That's great. Now let's see if actually the implicit function rule worked. So implicit function rule tells us take the derivative of this function that you have with respect to x, and just take the derivative of this function that you have with respect to y. Okay, well, what we had in the beginning was this, and it is not much of a function. But okay, so we can take the derivative of this with respect to x because it's just 2x, and we can take the derivative of this with respect to y, just considering y not as a function but just a normal variable. So using formula, the y prime x was supposed to result in something like minus a fraction. And then here what we have, the derivative of the thing with respect to x, it's 2x. The derivative of the thing with respect to y is 2y. So the thing, what I call the thing, is this. The derivative of 1 is always 0 with respect to whichever variable. There is no variable in 1. Okay, great. So this is equal to minus fraction xy, and that's it. So we got the same result. I just proved you that it works. You should tell me this is not a proof. If we just considered one example, we should give a proof in general, but I don't think you actually want that. So it works. It works and you can just really use it. So with I think I need to show you another example. Okay, yes, I have one question, or not a question. Minus x divided by y is equal to 0 in total. No, minus x over y is a derivative of y with respect to x if we are just given this implicit function. Is that okay? No? Ah, well, what happens to 1? We were just taking the derivatives of both sides, and the only thing that could happen to 1 is it becoming 0. But it doesn't mean that minus x to y is equal to 0. It means that, well, the derivative of this left part is equal to the derivative of the right side, which is 0. Yes, in this case, we can say that the equation has to hold, right? We're just taking the derivatives of both sides. Well, you should just think that what happened is we were taking derivatives, and that's how we managed to express and extract the y prime x. That's it. Okay, so now I'm giving you, oh, maybe I'm not giving you. Technically, it's our break time in 2 minutes. So, oh, let me just show you another example. So then it's easy for you to solve the other things. So let's take x, I'm just gonna take the same, but y squared equals x. So for this one, it's quite clear how would we proceed using this, taking first derivatives of both sides, but how would we proceed using the formula? Because here, the derivative of left side, like left side has x and the right side has x, so what you're just supposed to do is move x to the left and have something like that. So this is the standard form to start calculating to start using implicit function formula, and we're going to have, let's write it the same way. So we're gonna have fraction of f prime x f prime y, and here minus, don't forget. So that will be minus fraction with respect to x. Now what we have is 2x minus 1 because we have this part, and with respect to y we still have 2y. So it will be like that. Before, for example, solving this using the formula, we'll have to put everything to the left and leaving on the right side a constant or a 0 if we don't have a constant. Okay, great. So wait a second, I'm stopping the recording.